Okay, hello and welcome to the PML School. We are now in our 19th session and have only one further session to go until we go into a summer break. Today we are showing an example from a preclinical setting where you may not have systemic exposure data. That means you don't have any supportive drug concentrations available and you are just bound to effect time data to analyze your compound. As usual, this example has been taken from the book of Gabrielson and Weiner, and this example is called PD26 in that book for your reference. Please note that this will be our last example taken from this book. Our series will continue with examples from other references. I will talk at the end of today's presentation about our plans for the next series of PML School webinars. For today's sessions, as usual, we will make available the model files, the slide deck, and the recorded session to our forum, from where you can pick it up after the event. During this session, if you have any questions or comments, please use the Q&A console at the right-hand side of the WebEx console. We will come back after the presentation to deal with those. So let's see. In today's example, we will be analyzing a new antibacterial compound. In the in vivo test, we have 4 groups of Vista rats, where for each animal, 10,000 unit dose of a resistant bacterial strain was injected into the bloodstream. Then we had 4 dose groups with 1, 2, 4, and 8 micrograms of the antibiotic each that was given to the animals as an IV bolus. Blood was then drawn at selected time points to determine the bacterial count. So this is the data actually. Here are the curves for all 4 dose groups. And I'm showing mean data for each group starting at 10,000 units. And depending on the action of the drug, the bacterial count is decreasing over time. And after 5 hours, roughly, the bacterial count is increasing again. One thing to notice here in this exploratory plot is that we have a pretty wide range of effects spanning 5 orders of magnitude. And this is unusual for response time data, and that's also a reason why I'm showing the data on a semi-log scale. So this is the data that we want to model. Let's have a look at the model. So this is the model that we want to implement into Phoenix Win-on-Lin. It's a simple turnover model with linear stimulation of loss. So we have the production of bacteria, of the bacterial count N, and that is governed by the first order rate, growth rate constant Kg. And the killing of the bacteria is dependent on the amount of drug, and with kill rate Kk. So this is really simple, so let's go to the model itself. Because the model is so simple, in this particular case, we are not showing the built-in options that we typically do, and also we don't show any graphical model builder steps in Phoenix Win-on-Lin, because it's much, much shorter to do everything just in PML. You will see that there are some ways in the built-in options to specify all of this, but it also typically adds a PK part to the model, which adds lots of lines in the PML code, so we want to avoid that, and therefore we go directly into the PML code. So this is a textual model. Maybe we start, let me see. I have this one. So we have these 2 equations that are important to implement the code into PML. So we have a simplified construct of the PK, of the pharmacokinetics of the drug, because we don't have any drug concentration. So we express this just with the first order elimination of an IV bolus dose. So the amount of drug D is then dose multiplied by an exponential function with the elimination rate constant Ke and the time t in the exponent. That's the simplified pK, how we express it. We also describe the turnover model with linear stimulation of loss with this differential equation. So the change of the count of bacteria is then described by the growth rate Kg multiplied by n, by the bacterial count, minus the kill rate Kk multiplied by the amount of drug, and the bacterial count n. So when you want to implement these two equations into the code, you see this here a little bit highlighted, is exactly as we write the formula. You can do the same in PML. You just write it as it is. We start actually with the first line, a covariate statement, dose group. We use this statement here to introduce the 4 different dose groups. So behind these dose groups is the amount of the administered drug as an IV bolus. And with the covariate statement, we are just importing this data into the model. So this is just another way to link data from your input with the model by this covariate statement. You will see that, I mean, we've used it before and already, but this is really a good way to link data from your input data to the PML code. Next line, as we said, I mean, this is a simple PK description where instead of the dose, we are just taking the dose group explicitly here. And so it will take the individual dose amounts from the input and multiply it with this exponential function. And the next line is actually the differential equation, like we have it expressed here. Just a little bit different parameter names, but K1 equals Kg and Kk equals Kk out. Then the next one is a sequence function, n equals 10,000. Here we assign the initial value of n, the count of bacteria, and maybe this is a good time to explain the sequence statement in brief terms. In PML code, usually all statements are non-sequential. That means they are not taking action at a specific point in time. And that's also why the order of statements in the PML code typically doesn't matter. But if you have a time-based model such as that what we have here, where we see change of effects over time, and you want an action to be executed at a certain time point, in this case, at time equals 0, just to initialize the model, you simply use the sequence statement like we did here. Now, what that means is when you go through your data set, when the PML code processes your data set, you start with subject 1 at time 0. At this time, the sequence statement is executed and sets the initial value of n to the value of 10,000. That's what it does. And while processing, while it's going through all the records of your input file, it does the same sequence operation for every other subject in your data set. I hope this clarifies a little bit this statement, the sequence statement. The following statements after the sequence are pretty usual, pretty clear. We use a multiplicative residual error model for the observation of bacterial counts. Why multiplicative and not additive? Because as you've already seen in the exploratory data plot, our response data spans several orders of magnitude from 1 to more than 10,000, where a multiplicative residual error model is more appropriate. Finally, there are these 3 lines for the fixed effects, so we initialize those values with those numbers. That's the PML code. How do we get to initial estimates? The growth rate constant can be estimated from the upswing arm of the curve when the drug has been eliminated. We just take the difference of two bacterial counts and divide this value by the time delay between those two time points, between those 2 points. To achieve that, I will show you how to use the NCA object for this. Similarly, the kill rate constant can be estimated from the downswing arm of the curve. Here, the bacterial growth can be neglected and the kinetics are determined by the kill rate. That's shown here by this differential equation. An analytical solution of this differential equation is given by this expression here, where you need to have two bacterial counts and divide by the accumulated exposure between the 2 points. So we need AUC. To get the AUC, we would need to simulate the PK and run NCA on that profile. And that's what I will show you in the demo as well. So for the PK, for the simple description of the PK of the antibiotic, we simply assume a first-order elimination of the IV bolus dose with an elimination rate constant that we initially set to 1. That's the 3 parameters from our models that for which we need to have initial estimates. Next slide. So because the PML code for this simple model is really basic, right? I thought we can do a bit more PML coding for the simulation part of this. So in this example, we will code multiple dosing. And if you remember past sessions, in previous seminars, we have always used a separate dosing table for the simulations, or we have used the input options to specify multiple dosing. This was what I thought extremely simple and straightforward, easy to use, but for our simple model here, these options are not available. Because you need to have a compartment, a PK compartment, to specify those called dose points. In our simple model here, we do not have any PK compartments. We just express our PK in very simple terms. Therefore, we need to have code in place that defines these multiple doses in PML. So how can we do that? Let's see. We need to account first for accumulation. That is here shown in this series. If you think about it, after this single dose, when we dose a second time, we still have a bit of dose remaining from the first dose. This needs to be taken into account. Now, after the second dose, when you dose a third time, you need to take into account remainings of the first dose and the second dose, and so forth. This can actually be expressed in this accumulation series. Now for this series, there's a solution in place, and this is shown below, which is really the general equation to calculate PK after multiple doses for, in this case, IV bolus administration. And as we know it from PML, to get this formula into Phoenix Vanillin, you just need to enter it as is. And that is shown here, where you see this, the PML code for the simulation. This is shown here. It's much the same as you see on this equation. Now you need to have a few other parameters or numbers for this equation. So you need to have a dosing interval, tau, it's given here. You need to tell the code how many doses you want to apply in a multiple dosing scheme. In this case, it's 3. You want to know which dose you're currently simulating, so the nth dose. This is done by this sort of if statement. And you also want to have the multiple dose time. And the multiple dose time is just expressed with this equation. And what you can also have is here, just as a secondary parameter, if you will, an accumulation factor. So you see, I mean, how much of the fraction you are accumulating over the multiple dose scheme. This will appear then in a secondary worksheet of your results. This is everything we need for our simple model. So let's go and just do this. Let me share Phoenix application. Cheryl, can you see my screen?
Yes.
Okay. So let's see. So we have here the PD26 data, where we've got time, then bacterial count. We have a dose group, which is actually the amount of the administered antibiotic. And then we have different groups, 4 different groups. So let's just plot the data here quickly to see what that is. Time on X, count on Y, and group on that. That's okay. This is our curve, and you see this doesn't look very nice, so we just need to go to our Y-axis and put on a semi-log scale. Maybe we want to express our numbers in this way, so we just have real numbers instead of the exponential numbers, and then maybe we want to plot a little bit wider. Okay. So this is our data. Oh yeah, the tick mark is a little bit too small. Okay, now we have, this is our plot. So we've got these 4 dose groups, 1 microgram, 2, 4, and 8 micrograms. For the initial estimates, we said we want to get some slope data from the downswing and the upswing arm. And I'll show you how you can do that with the NCA object. So we just send our data set to an NCA object. And in this case, you have different model types, and we just take the drug effect model type, which allows us to define 2 slopes in your data set. So you have time and count. Time is X and count is Y. I guess we need to provide a base threshold, therapeutic response. Let's say 10,000 and 1,000 as a threshold. And then what you have here is a slope selector. Oh, wait a second, I need to sort by group. Dosing. No. 0 and therapeutic response, that's all right. So slope selectors, here are our slopes. So a downswing arm and an upswing arm, and we want to calculate using time range, and we look at on a log scale. Slope 1 is a log, and we take the first value and the third one for this first slope, and for the second slope we take also time range this point, this one. Come on. And this one. So you've determined 2 slopes, slope 1 and slope 2. And this we can do for all 4 different dose groups. So I just slope 1 takes a little bit of time, but you get some good numbers out of this. And for slope 2, that looks all right. Slope 1, time range for this one and this one, and for slope 2, log, time range, I take this and this. And the same for this one. Do this. Okay, that's fine. So once you have defined your slopes, you can also run automatically. You have slopes for the downswing arm and slopes for the upswing arm. And for the upswing arm, we said this is actually our initial estimates for the kg, for the growth rate constant. So roughly it's 0.1, 0.2 type of, let's say 0.2 as initial estimates. But for slope 1, we actually have to divide this with the AUC. So what we actually would need to do is to run a PK simulation, just to get a profile. I mean, it's a simple profile, but let's see. We just say we send our data to a Phoenix model where we have a PK, not a population one, with a micro parameterization intravenous, one compartment. We can leave everything as is, and we just want to run a simulation with a sort by this, and the dose amount is A1. The dose amount is A1, and we just run a simulation, maybe 50 points over 25 hours. We just want to get C. So this is just a simple simulation for an IV profile with the dose amounts as we have it in our data set. And this looks like this. Oops, yeah, too many. What is the dosing? The dosing, yeah. It takes too many doses. No, we need to provide the dosing in a separate sheet. Sorry. 1, 2, 4, 8. It was just, I'll show you what the error was. If you look at the data here, the dose amount is on every time point. There's a dose amount, and that's what the simulation is taking on. We just need one initial dose at the initial time and at time 0. Let's do this once again. And look at the simulation curves. This is it. These are the 4 curves. And this is the data actually. These are the concentrations predicted. So we send this to an NCA and to NCA model. In this case, it's plasma data with an IV bolus dose, and we have IVAR is time, the independent variable, DV dependent variable is concentration, and we take group as a sort key, dosing by group, and we know this for 8 at time 0, 0, 0, 0, and we just calculate the NCA, and then in the summary table, because we have taken the first 3 time points from the data, we have here an accumulated AUC, which is for the first dose group 1, it's 0.6 roughly. For the second, it's 1.3. For the third, it's, wait a second. Come on. It's 2.6, and for the fourth, it's 5.16. Let's go back to the slopes. So this was roughly 1 divided by 0.6. This is roughly, I mean, averaging over everything, it's around 1, around -1, and this is 0.2. So these are our initial estimates for the model. So if we have these as initial estimates, we can actually model our data. So we can send our data set to a Phoenix model object. In this case, this is a simple model, right? And I guess for this model, we go directly to the textual part. Because we don't need actually the the built-in options. Because let me go to the built-in options just to show you. I mean, what kind of lines you would get. Your PK indirect would be the right choice as a type, and we would model a stimulation linear of the loss, right? And if we now go to the textual, you see there are just too many lines of code that we just don't need. So we just delete everything here. And I've got the simple model as a text file. You know, this is actually the text file that we will upload to the forum. So I just copy it from this text file and paste it into this field. And here you see exactly the same text as I've shown on the slides. Just corrected the parameter name so it was more consistent. But it's much the same. We have already put in our initial estimates, 1 and 0.2. We just need to map our data. Time is time. N-ops is our count. And actually, we can run it under population mode if we say we go to a naive pooled method. We try the hashing, and we put our group as an ID column. So this assumes that there are no between subject variabilities among those measurements, and we just take it as it is. Okay, that's it. We can just execute our model and see the fit. So here, lots of plots, but we are just interested in the fit itself. Again, I mean, this is a linear scale. We need to double-click on this plot to pop it out of main window, and put it here on a logarithmic scale. We also want to have our axis with real numbers. Maybe I can say this is our count as axis label. We can also use different axis label here, time, and we make it a little bit wider. Okay, and that's it. That's it. So this is a fit. It's not really perfect, but it somehow scattered across those data points. Some are here. We've got one run here and a couple of runs over here. Let's have a look at our theta table, our fixed effects. These are our estimates: KE of 0.5, KG of 0.1, and KK of 0.8. With the CV percentile look really reasonable, so I guess with this simple model, this fit is not too bad. So what we said is this was very quick and easy, you know, not a very complex model. Let's do a multiple dose simulation. What we do there is we just copy this and paste it back to the model, back to the workflow. And there's one thing you should not forget when you run simulations. The first thing you should do, you know, you copy your model and paste it back to the workflow, but the very next step should be go to parameters, fixed effects. Here's the model once again. These are still our initial estimates, but these are the fitted estimates. So you need to accept all fixed and random, so you get the true numbers in your model incorporated. So that's it, but we need to take care of the description of the PK, because we have to account for accumulation, and this is, I'll just take it from the text file. Again, I mean, these text files will be uploaded to the forum. You can take it directly from there. So I'll just delete this one and paste the code here. So what we have is here a tau value. Maybe go for 24 hours and 3 doses. For the simulation, the nth dose is just expressed with this if statement. We've got the multiple dose time, and then this general equation for the multiple dose PK. Also the accumulation factor that we've calculated here. That's that. So we've put those in place. Maybe with the plots, you know, we don't need all the plots for the simulation, so we can disable everything. We just want to see the individual simulations. Then we go to run options. We can switch off the population mode. Do the simulation. We look maybe for 1,000 points, max range maybe 144 hours. Now, what we have here, we have an observable N. This is this is a predicted value of the bacterial count, and D. So we want to see N and, or better, D and N. These are the two predicted values that you want to see. In our simulation, what else? Yes, we need to group by the group variable here. That's it. So let's run the simulation. And we've got 4 individual simulations for each dose group 1. And just to look at the secondary, this is the accumulation factor with a KE of 0.5. There's not much accumulation of after 24 hours, almost nothing. So yeah, it's just 1. And if you look at those values, okay, we need to put this on a logarithmic scale. So here is in blue is the bacterial count, and in yellow the drug amount for the 4 different dose groups. We can maybe put a threshold line at 1 threshold, right? Okay, this should be reached until you see really a killing of the bacteria, and that's only shown for the large group, for the 8 micrograms dosing group. Maybe what we can do easily now, you can play a little bit around. Okay, we say we change the dose interval to 12 hours and the number of doses to 6. Simulate once again. I mean, this is just now, I mean, trying several scenarios out, what you think is best. You can also change the dose amounts if you want. So this looks a little bit better. Now there's a little bit of accumulation actually. Let's look at the secondary. Oh no, yeah, that's just not very much. Okay. Anyway, so this is, we can actually, what we can do is, this, I mean, with these very low and small numbers, we can cut actually. Let's say we go down to 0.01, and maybe here we go to 100,000. That we've got some plots showing like this. Okay, simple simulation. Here you can choose different scenarios to see what you can get out of this. Now let's go back to the slide deck. Let me see. Okay, so this was a demo. So this was, we've seen that we were able to fit the model quite well with our simple model, but based on the encouraging results from this first study, there was another study of the antibiotic undertaken. And here there were 2 differences to the previous study. First of all, what you can see here is a vehicle group, a control, where no dose was given, just a vehicle was given, so no drug. So you can measure unperturbed baseline growth. And this is something we can take into account in the model. And also, this maximum dose of 8 micrograms was reduced to 6 micrograms, so you don't get too much of a decrease here. So with the extended data set, as I said, we can actually augment our simple model with a more accurate description of baseline growth. So bacteria will grow until a maximum bacterial count in the system is reached. And when the number of bacteria approaches the steady state level, which is expressed with the parameter N max, the growth will stop temporarily. And so this can be achieved by inserting this expression into our turnover model. As soon as N equals N max, this fraction becomes 1, and the whole growth or input part of the turnover model will give 0. So that brings the bacterial growth in the model to a stop. And as you might have expected, the implementation of this little extension of this model into PML is really straightforward. Look at this. It's just taken as is, as usual, so not a big deal. We have introduced a new parameter, nmax, for which we need initial estimate, and this is just taken from the exploratory data plot. You just look, at this last value, and it's about 33,000. So this was just taken directly from the plot. So that's what we want to model now with in Phoenix. Let me share my model once again. So we just take our simple model, copy it, and paste it back to the workflow. So this is now our baseline model. And for the baseline model, first of all, we have to replace the data set. It's now the extended data set. For the model, we just have to put in here another statement, another expression, n divided by nmax. This one, kgn, and we have to add another fixed effect, nmax equals c colon 33,000, and this is initial estimates for the max bacterial count. Okay, this is it. Anything else? No, this is just a little extension of our model. Let's see. We just want to fit the data. And here we are. So you see the fits look very nice. I mean, it's a pretty rich data set, I have to admit. I mean, this is really lots of data points, and the curves do a very nice job in fitting those data points. Let's have a look at theta. Here are our estimates, a little slightly different from the previous run. But look at the CV percentage, the variation, coefficient of variation. It's much sharper estimates. So this is really a nice model. And again, we can use this model to do a simulation. So we copy and paste it back to the workflow and just call it as such. This is a baseline simulation. First thing, always not forget, accept all fixed and random, yes. And then we just say this is a simulation with 1,000 data points, max range maybe 144, and D and N, that's what we want to see. We have to go to the model and replace this one line by the lines from the simulation model. This is it. Plots, we don't want to see everything, we just want to see this one. Did we say group by sort? That's it. Now we can run the simulation. Okay. 4 different simulations for each of the dosing groups. Let's see. Okay. And here we are. Once again, we need to do this once again. Logarithmic, custom, something like this. Okay. So here we have our unperturbed growth, which actually, converges to the maximum bacterial count and max. And here we see the decline. So this is a way how we can do simulation with these simple models. I guess that's the end of my software demo. Let's go back to the slides once again. So just to summarize and look at the results once again. This was a simple data set with a simple model. We've got nice fits, pretty sharp estimates. But when we move to our extended data set, the results are much better with much lower CV percentage, and also when you look at the fit of the data points, much better. Okay, with that, I'm at the end of the presentation. So let's open the Q&A panel. Let's see. I guess I can't see question. Yeah, if you want, I mean, you can just start entering questions into the console. If there are no questions at this point, let me just move on because I've got some announcements to make. Oh yeah, here's one question. Is it necessary to use log for calculating slopes for PD? Yes, that's necessary. That comes from the conversion from the differential equation into the analytic solutions. We need to get the logs of those. Yeah. Okay. Let me move on now here with the slides. So just a reminder. You should have, I mean, you have access and you should make use of it to all materials that we have accumulated so far. This is the 19 sessions, as I said, and we have on our forum more than 30 topics. This includes not only the materials, but also the Q&A, question and answers topics. And we have right now 18 videos on our YouTube channel for all the PML School sessions. 19th will be added later on today. So please make use. Here are the individual links that will get you there, and you just need to pick up the material from there. So this next time we have a session, our last session of this series on August 10th. Where I'm going to present an example for transaction modeling and how to assess the number of transit compartments. So this will be the first session of the PML School where we don't use an example from the Gabrielson and Weiner book. So I'm going to show you a Phoenix implementation of the Freeberg model for chemotherapy-induced myelosuppression. And you know, there I will be able to actually share the Phoenix project file, so you don't need to build up your models and simulate data curves on your own. Everything should be coming then with the Phoenix project file. But then after this session, August, September, rest of August and September, we go into a summer break. And we will continue with a new series of webinars, 6 webinars until the end of the year, starting in October. And let's see what plans we have there. I mean, based on some feedback that I've received, we are starting with user presentations. So because I think we've covered by then 20 sessions from the Gabrielson and Weiner book, we've covered everything that we've seen in support for, you know, model-based questions around Phoenix, Win on Lin. So maybe you've got some ideas, some new ideas and models that you want to bring up to the audience. And what I would suggest is you just send me a model or your idea to my email address shown here, and then we can discuss and maybe refine the idea or the model so that you can take this for live presentation at the PML School. This must not be a very difficult model, but as I said, as you've seen in the past sessions, there's typically 1 or 2 tips or tricks in a PML model that other people might be interested to see, and you want to share with others, and that's what we'll give you here a panel to show this to a live audience. And just, you know, send me your feedback to bernd.wendt@certara.com, and we can pick it up there. At the same time, we are starting an alternative topic. I've talked about this once before, the non-mem to PML comparisons. You know, non-mem is also is another very popular modeling software, and there are also models around for this software. And what I want to show you in those webinar sessions is how you can translate from NM-Tran, that is a non-MEM modeling language, into PML. So we are setting up non-MEM models as well as Phoenix and LME models side by side, and run this within Phoenix, and then we'll compare the results to see where are the difference and where are the commonalities. And this we will be starting as well in the next series starting in October. With that, I'm at the end of today's session. I want to thank you for your attention and hope to see you back in 2 weeks' time. And yeah, bye for now, and you may disconnect now.